Thanks, Scott. Just a little higher. By way of introduction, I came here in '91, and I was up here at the Lake Region in January of '92. And I remember there was a speaker here from USGS, and if people old enough to remember, the lake level was really low at that time. And there was a lot of talk about how do you get water into the lake. And this gentleman from USGS said it would take 25 years of above average precipitation to get the lake level up to where people wanted it. Well, after that, I started following it, and by November of '93, it was 7 feet above what he had predicted. '93 was an extremely wet year. It looked like there was a bullseye here. So I think I was here in '97 talking about flooded septic systems, because the lake kept rising and flooding out houses, and so they had to abandon the septic systems. So I'm going to talk about tile drainage today. We did a tile drainage design workshop here in this, well, not this building, the next door, about 5 or 6 years ago with my colleague Hans Kandel, who will be here tomorrow. So I wanted to talk about tile drainage because I know it's been coming into this area more and more. So just so everybody in the audience knows, what is subsurface drainage? We call it tile, but almost everything going in today is perforated polyethylene plastic, usually 3 or 4 inch in diameter are the laterals, and it's varied anywhere from 3 to 4 feet. Typically in the Red River Valley, it's about 3 to 3.5 feet laterals, and it's meant to control the water table, as it's shown in this graphic, which I got from my colleague in Minnesota, Dr. Gary Saney. Subsurface drainage, where is it used? Anybody in here have basements? Tile around it? Well, you got tile drainage. You are intercepting that groundwater that might rise or any of the storm water and diverting it into a sump so it's not flooding your basement. But more and more I see in road construction, it's used quite often to reduce frost heave and damage to concrete. I remember about 25 years ago, if you took that hill out of Valley City on 94 going to the west, up that hill they always had, it used to be up and down because there's water problems coming out. They tiled it at that time. You don't see that happening. I know between Moorhead and Barnesville in Minnesota, there's about 8 miles that they tiled there because they had problems with water. And more we see it used to control frost heave. And frost heave is caused by 3 things. You either got water, you got cold, and you got clay soil. You can't do a whole lot about the clay. You can't do a whole lot about the cold weather and the frost penetration, but you can get rid of the water so it isn't expanding and pushing up and down. So we noticed in tile drainage that a lot of farmers with their marketing, one of the first things that started in the mid-90s was to tile their yards so they could get in with their semis to load them with drain. They were getting stuck in these frost heaves. So the way you get rid of it is tile and get rid of the water in there, and from there it kind of moved out into the field. Ulster-Earthen dams. There's an extensive tile drainage system in Garrison, Fort Peck, Oahe to control seepage water, so it doesn't wash out the bottom. And of course on agricultural fields, and there's a lot of other areas. So it's used extensively to remove excess water in the soil, not surface water, but in the soil. So why do we have high water tables? Well, usually you have an impermeable barrier, compacted clay, or it can be farther west, it can be fractured rock. And there's water on top of it, but it's always seeping through, but it seeps through very slowly. And eventually, if you get a lot of rain, and it infiltrates, the water level will rise. Sometimes it'll rise all the way to the surface or near the surface and just saturate everything. Given time, it would eventually seep away, but I don't know if you can wait 90 days in an agricultural field for that to happen. So it causes problems up here and people get stuck and buried. So that's kind of the basics of why we have to control the water table. So it's not a new thing. The first documented case of subsurface drainage was in upstate New York in 1836, a guy named John Johnston. He came from Scotland and kind of brought some of these ideas with him from Europe. And all of his neighbors told him, you can't drain, he was getting 20 bushel wheat on this 80 acres, and he knew it was a high water table, so he tiled it, and everybody called him a fool until the next year he got 80 bushel wheat. Everybody became really interested in controlling the water table. You might be surprised to know that in 1858, quite a few acres in Central Park in New York City were tiled because one of the reasons they didn't build there was a swamp. And they couldn't get the buildings built. And then it ended up as a park. Mold ditchers. All they are is really a big cylinder attached to a plow, and you pull it through, and if you've got a muck soil, you can create a hole and it'll last for a while in heavy clay and drain it out. That's one of the simplest ways. Some soils you got to do it 2 or 3 times a year, and some would last the whole year. But essentially, it provides an outlet for the water to flow out of the field if you've got a ditch. But there's been a lot of different, we call it tile because that was one of the most common material they used to make these circular pipes. But if you're really interested, the Romans were doing it around the time of Christ. These are actually excavated from in the city of Rome. These are old tile, and you probably heard that Rome had 7 hills. And in between those hills were swamps. They couldn't build there until they got rid of the water. So they were tiling and surface draining quite a bit in order to, and they were tremendous engineers. So it's not a new concept. It's just that it takes a little while to get up into this area. And if you're really interested in upstate New York, there's an actual museum on tile drainage. And they got over 350 different types of tile or drainage pipes that were installed. And some of them are made out of clay, some people that were poor enough but had a lot of saplings around would actually dig and put trees down or put saplings down in the bottom of the ditch to provide a drainage way for the water to move out. In this area, the earliest I can find is there was research in Crookston, Minnesota, not too far west or east of here. And at that time, they were tiling southern Minnesota. We had a lot of, let's say, manufacturers of concrete tile that were putting out questionable materials. A lot of it was collapsing. So the state of Minnesota required them to test it. So that's what all these are the different manufacturers, and these are the tile they put in. And they showed that it could work and that it was worthwhile. The problem was at that time, it cost around $25 an acre to install the tile, and you could buy land for about $10 an acre. Well, if you're a smart farmer, what are you going to do? You go buy more land rather than invest in the tile. Just to back that up, there was tile put in the 40s when they had a wet period, again in the 70s, and it really started to take off in the 90s. Actually, in my record that I inherited from previous workers in extension, there was some tile put in by Pekin and some other in this area years ago. I think that one site we tracked down is under the lake right now. So we progressed quite a bit. I took this picture in 1999. This is a commercial outfit. And the one thing I want to point out is they still look the same. The plows look the same. This is one of the technological advantages is that we plow in this pipe. That white on there is actually a sock for that sand from, this was by Hunter in North Dakota. But I wanted to point out that back then they were using a laser map for guidance to set the elevation. I don't know of anybody doing that anymore. More and more we're seeing GPS, which is located right over the point of the plow. And this is a farmer that we worked with that was putting in his own, but almost, I think all of the commercial people are using GPS, and it's all tied into a system in the cab that can actually almost adjust on the go. And I don't have enough time to go into all the details, but we progressed quite a bit. And so these technological advances of using GPS, electronic control, electro-hydraulics, the availability of farm plows has really made this subsurface drainage more acceptable in this area. So the driving forces behind it, high land prices. If your land is worth $7,000 an acre and you have to buy more land and it's got wet problems, if you invest $1,000 or $1,200 in subsurface drainage, it's probably not a bad investment to improve it. Because acquiring more land is becoming more difficult. It improves the land management options. You've all heard the salinity problems, right? And proliferation of soybeans and corn, neither which like salt-affected soils. You know, wheat is a little more tolerant, barley's more tolerant, but you can't. Soybeans are really not tolerant, and so if you want to expand and grow that high-value crop, especially with the new crushing plants coming in, you got to get rid of those salt. That's some of the land management options. That improves your crop selection, and you get more consistent production year in, year out. I got studies going back 60 years showing that the coefficient of variation of yield is much less with the subsurface drain field than it is with, you know, just going by Mother Nature's wet and dry. So we know it controls the water table. We know from a lot of research for many years that it increased the yields. Now, the big argument is how much does it increase it? If you look over a 10, 15-year span, and I think Hans Mandel could tell you more, we see that the average yield is around 10 to 15% over that time period. But there's years when it can be over 50% when you got a wet spring or a wet fall, and you can't get in to harvest it or some things. And then there's when you got the dry years, it basically kind of wash. You may not gain anything. And a colleague of mine looked at tile drainage in the Crookston area for 100 years and determined that 33 of those 100 years, there was no tile flow at all. There were some that were, you might have some flow in the spring, you might have some flow in the fall, and those are usually the two big periods up here. So it will control salt. The one thing about salt, and I'll talk about that a little later, is that they accumulate, and you want, the only way you really get rid of them is you have to move them out. And it maximizes the root growth if you have the soil depth. So how does, just so everybody knows, how does tile water get into tile? This is ground surface. Typically, we've been monitoring now for almost 20 years. We found in this area, not necessarily in Ohio and other areas, but up here, typically in July and August, the prophets pull out enough water out of the soil that the water table is below the tile. That's what these little black lines are. So if it starts raining, say next spring, or you get snow melt, it infiltrates, the water level starts rising. And this white here is the capillary fringe. That's just where it's almost saturated, but not quite. So it's only when the water table actually gets to the tile that it starts to actually flow. Research has shown that almost 70% of the water comes in the bottom half of the tile. doesn't come in the top, it comes in from the bottom. And as you get more rain, it'll form a mountain between them. And of course, this will drain out whatever flows into it, but then it forms a mountain in between. And the water actually takes a circular type of path to get to the top. Especially from here, it actually goes down. And believe me, there's lots of mathematical papers and studies showing this, but that's typically what happens. And then from a design point of view, when we're trying to figure out on a particular soil how far apart, we don't want that water table to get more than a foot from the surface, because a lot of roots are up here, and we don't want to saturate it. So we try to design for a design point so that when you get these big rain events, that the water table only gets to within a foot of the surface, so you keep oxygen in the root zone and keep the plants happy, not selfish. So after it stops, it ends up like this. And 1919. Okay. In 2019, the fall, we had it was really wet, right? Everybody remember that? So we went into spring, we had tile land sitting like this. So the next spring, if you got any rain, the tile would flow. And if you don't believe me, this is a chart that I took out of a book from 1911 from Iowa State University. And the scale here is, this is 10 feet, each of these blocks, and this is 1 foot. So this is ground surface, and there's a whole series of observation wells put in here on these two systems, these transects. So on April 13th, when they measured, there was the blue line shows what the water level was at these different parts. Well, on April 14th and then on the 18th, those 2 days, they got 1.6 inches of rain. So on the 19th, this is the water level that they measured in those observational wells on both transects. And then they came back, whoops. On the 20th, it already dropped almost a foot. That's what this line is. I thought they had another color on it. But anyway. So this is actual data. We've been monitoring tile field. These are in Red River Valley. I think it would be the same up here. And we have these observation wells. And this is just an example from 2013. And the spring of 2013 was really wet. This purple line here is an undrained field. It's just natural runoff. So you can see where the rain events happen. The other one is the fully drained, and this is tile land. So you can see it only got to the tile because it had removed water previously earlier. So when we got these heavy rains in here, it barely got up and the tile barely flew. So we've noticed this a lot. The thing that's interesting is in July, when the crop really gets growing and starts sucking water out, it's actually mining that water down here. And you see the slope of this? This is the water use of the crop. They're almost parallel, right? But there's about a 2-week differential here between the undrained field and the drained fields. And this is, the tile line is right here. So this blue line, we were experimenting with subirrigation, actually running water back into the tile to see if we could put water back into the soil. This is fairly typical, is what we notice, is by July, when the crop really gets going, it's pulling water up. And there is an upward flux of water from down here. And why it's flat here is you only have an observation well down to 6 feet. I'd like to have put them down to 9 feet to really see what was going on, but they're only 6 foot. So this was fairly typical when you have a wet period. So key design parameters, you gotta have a water outlet that's put in subsurface. Now, when Hans and I talk about a water outlet, we're talking about putting water into something where if there's dissolved minerals or salts, as they call them, they stay in solution and that water keeps moving and it moves to some location like the Red River, to the Cheyenne, the Maple, someplace where it keeps moving. If you put it into a dead end, evaporation in the summer times is gonna pull up the water and leave all the salts behind. And that's why we have salt problem. So when we talk about a water outlet, we want to put it someplace where that water keeps moving. We all want it to end up either in the Gulf of Mexico or in the Hudson Bay, ideally, because the thing with salts is once they're in water, they stay in water. They don't settle out. And then we talk about a drainage coefficient. That's how much we want to remove out of the soil in a given 24-hour period. We usually talk about 3/8 of an inch over an acre. That doesn't sound like a lot. It's just a small amount. But within the soil, in the clay soil, that 3/8 of standing water will occupy around 8 inches in the soil between saturation and field capacity. So it's a design point. It's the amount that, as an engineer, we need something to guide us in how to determine the spacing between the tile and how much water we want to remove. So that's what our drainage coefficient is. And believe it or not, there's no real scientific basis behind this. It's really based on the precipitation. In this area, 3/8 of an inch works really good. You go to Ohio, in some places they use 3/4 of an inch. In some places they use an inch because they get 50 inches of precipitation. We get 20. It's all on how much rain and precipitation you get. And just by trial and error, we found that even farther west or out here, you could almost use 1/4 of an inch worth. So remember, it's a design point. And then the field characteristics. We always want tile works best if you've got good surface drainage. You can't eliminate the surface drainage because it's only removing water out of the soil. It's not removing the water that's on top of the soil. And then we need a good topographic. We need to know where the low spots are, the outlet elevation. This is extremely important. Tile grades. And so we know what the slope of the field is, so we can set out what the slope of the tile is. Then we need a real good idea of the soils, which more and more we can get from, as a starting point, we can get soil survey, the soil survey information, the web soil survey, NDSU. And then based on that, we can calculate for a given soil in a given area, what would be an appropriate spacing between the tile. And then from there, we can design where the main, sub-main, and so forth go. So I gotta tell you, if you are contemplating putting drainage, you really need to visit the NRCS with their wetland maps, because you can't drain a wetland. You can go through a wetland with non-perforated tile, but you can't drain it. So you need where those maps are. You got to visit with your local water boards. If you're tiling more than 80 acres, you got to get a permit. And the State Water Commission is concerned about statewide significance. I think the whole Devil's Lake Basin is considered statewide significance, but still it's up to your local water board now. You don't need their approval. I should have taken that out. The other thing is, I think it's up to local water boards whether they want to require you to, even if you tile less than 80 acres, they want to know about it, where the outlet is. You don't have to get a permit, but they want you to notify. I think there's even a form on the State Water Commission website for how to submit that. They can't turn it down, but they just want to know where it's at. And those are some of the changes that took place in the legislature. And I always tell people, talk to your neighbors. We found in a couple of cases where neighbors didn't talk to each other. but they were both gonna tile a field and they could have saved themselves a lot of money by sharing an outlet. Sometimes it pays to talk to neighbors, see if they're gonna do something. And then, of course, the big one, and I'm no expert on fish and wildlife easements, but they can play a part in whether you can put in subsurface drainage or not. So we usually start with a topographic map. With today's GPS, you can generate these pretty easily. The important thing is what's the elevation of the outlet and high points. And then this just shows the contour lines. But you can see that the slope is generally this way. This is actually one of the topographic maps, pretty flat one that we use in as one of our demos in the workshop. So just to give you some idea of basic, if you have a field like this and you got a ditch, first thing you got to do is you've got to establish the outlet elevation. Let's say it's here. So the first thing is going to put in a main. And the outlet elevation sets the elevation for everything else. And you notice I put a slope on it. All time has to have some kind of a grade or slope on it so that the water flows, right? And once you got these elevations, then you can attach the laterals to it. And they gotta have a slope to it too. So let's say this is 1,000 feet and you got a 0.1% or 1 foot rise in 1,000 feet. So from here to here, there's a 1 foot rise, and this is 2,000 feet. And this has a 0.1% or a 2 foot rise. So this is 3 feet down. So you add 2 to that, that's 5. And then it's 6. So you got a 6 foot drop to the outlet. A lot of times the main is buried deeper. So that's part of the design process of laying it out. And I'll probably repeat this. There's no one correct way to tile a field. There are several different ways. Some are probably, every field is different ways that you can approach the problem, but you still have to recall that everything has to drain towards that outlet. You can get gravity flow outlets, that's ideal. It isn't in level land, that's hard to do. So you got a lift station that you got to put in. The ditch may be, the outlet from your main may be below the ditch. So I like to throw this picture up there because there's about 300 gallons a minute coming out of there, but that water is from the surface drainage here coming out of this culvert. So, and spacing is important. Like I mentioned earlier, we don't in Iowa in the mid-90s when U monitors came in, they found out that their grandparents tried to save money by stretching this distance farther than they needed to. And as they went across the field, they found out that the yields were going up and down in between the tile. And that's what set off a real tiling boom in Iowa, was to put another tile line in between and to correct the one that they had. So the U monitor made a big difference in tile draining. And this is an exaggeration. A lot of times you couldn't tell by just corn looked the same. It's just that the yield varied. Could have been 20, 30 bushel in between, just because of this situation where it got wet too. And so just to give you a general idea, the finer the soil, the closer you have to go with a 3/8 drainage coefficient, maybe 40 or 50 feet. With a sandy loam, you can go 80 to 120 feet. So it really depends on how easily that water moves laterally towards the tile. It makes sense, right? Water moves through sand better than it does through clay. So it affects it. These are just general recommendations, but you get the idea. So there's a lot of different pattern tile. This is parallel or pattern tiling. If you have a waterway, you might tile on both sides. Might have random or targeted drainage. And I know as I go farther west, we see more of this. The herringbone is not used as much as it has. That's more in, but it is part of the. You can see it's used in some of these situations. This is natural field done in the Red River Valley. Pattern tiling is pretty easy. You get out to the plow and you just go 2,000 feet across. You got your maze here. There's the lift pump over here. Actually, this is about the easiest to design these level field. And that's what it looks like from the air. You can see where all the tile lines are put in. The lift station was over here. In some areas, you don't need to tile the whole field, pattern tile. So we use targeted drainage. This is natural field. These are the drainage ways that are tiling on both sides. And the different colored lines and the different size tile because they're intercepting some of the flow that comes from higher elevation. So next thing I want to talk about is salt affected soil. That's not snow out there, by the way. That is salt. I think I took this picture east of Carrington, or west of Carrington, sorry. So that's what happens when evaporation leaves the salts behind that's in the water. It brings it to the surface. And the NRCS did a study several years ago in the Red River Valley, and all that red is potentially saline or salt affected soil. I don't have a similar map for the Devil's Lake area, but I suspect it's not that much different. Remember, this is potential. That doesn't mean that they all are. It's just that those are areas where salt have accumulated. So, as an engineer, I've always wondered why we have this unique area up here where we have all these salts in a rain-fed area. Because all the literature that I've said from around the world is all related to irrigation, salinization due to irrigation, because the irrigation water contains salts. And so there's always a balancing act. But up here, we got rain, which has no salt in it. So I went to John Bloom, was the state geologist, who wrote this book called Basin, North Dakota. And in there, he talks about the glaciers. I'm going to blame the glaciers for a lot of our problems. If you notice, at the last glaciation period, there was a big mound here, one here, and one over here. Now, what's really interesting about this is the Canadian Shield. This is all granite up here. This is all seabed out here. So the glaciers actually came down through South Dakota this way. And in this area of Saskatchewan and northeastern North Dakota, there's a lot of old shale beds. And the glaciers, like a big bulldozer, straight right across the top of them. And shale contains a lot of sulfate. So the glaciers came down, pushed everything down here. Minnesota got glaciated this way. And so they didn't get the salts that we get. And at its largest extent, old Lake Agassiz was about this large at its greatest extent. Now, Lake Agassiz filled and emptied a number of times, at least 20 times. There were interglacial periods where it melted, receded, then it moved again and kept moving back and forth. But you can see up here by Minot, actually Fargo's on the southern tip of Lake Agassiz, but it was a huge lake. And Lake of the Woods, Lake Winnipeg are just potholes in the bottom of it. And of course, Devil's Lake here. So when you look at the meltwater channels, meltwater all went this way and dumped into Lake Agassiz. So these red areas are glacial moraines and sands, but the yellow is sand. And so a lot of this water drained this way and carried a lot of those salts with it. And that's why it deposited. So any low area during these melting and dropped a lot of these salts. So some fields may have no salt, and you go a mile away, and then they have a bunch because of this up and down action of this water flow. And he even states in there they used to mine sulfates up in this area. So that's a lot of what we find in the outflow from tile. A lot of sulfate. So I don't know where it all came from. Now we have to deal with it. So just to give you some idea, just a month and a half ago, I was out on a farm field by Polk, North Dakota. This is 80-acre field. The nice uniform slope. This is a sloping field. It's about a nice uniform 1% slope. Got good surface drainage. But the farmer told me that he and his dad for 40 years have never made this field really pay, because in this area over here, there's salt creeping up. So where's the salt coming from? You have a nice slope like this. So looking at the general topography, and this is what I'm trying to get across to you, is that you got to look beyond your field. Here's that field, and this is to the west of it. And you see all this area? So whenever you get any rain, snow melting and everything, I suspect what's happening is water is infiltrating. There's some kind of clay barriers here, and it's moving this way and then outcropping along here and carrying those salts with it. That's the only explanation I can come up with, because it's like a continuum. So the only way he's going to get rid of the salt is to tile. And my colleague Naeem is going to go out this spring and actually sample this field to find out if he's got any, what the saline problems are down 4 feet, and if there's any sodic problems with that field. But the landscape has a big impact. So to carry this on, what's in the water? We had a research project from 2009 to 2013, in which we sampled 8 sites up and down the valley to see, and we took samples when the tile were flowing for 4 years to see what was coming out. So what we found is, when we look at the 8 sites, these graphs show you the range from here to here is the range of total dissolved solids or minerals or salts or whatever you want to call them that we measured. So it went from about 3,000 up to 10,000, and that's pretty high on this. And then this is 25%. Blue is 25%. Red is the top 3/4%, and then this is the last 25%. Now we had 2 sites. These sites were supposed to be selected to be salt affected, and we worked with the local soil conservation district to pick the sites. Unfortunately, these 2 sites were sandy soil. These were not salt affected, and the tile had only been installed in the previous year. So you can see there was no change on these, on no sand. But this site, this Richland site, had a wide range. And the other ones were very similar to this one. So that's the total amount of dissolved minerals that are in the water that was coming out of the tile over the course of those 4 years. And what a lot of people are concerned about is how much nitrate nitrogen was coming out, because that's one of the things with tile drainage is you will lose some nitrogen out through the water. Now, the interesting thing was that the 2 sandy sites had the lowest. It's 10 parts per million nitrate nitrogen, and it doesn't apply to tile drainage. Nobody's going to drink this water, but that's the limit for the Safe Drinking Water Act for consumption by humans. Well, you can see both of these were way below that, but the other ones, this one was really high, had a wide range, but a lot of the other ones were pretty low. And you can see what the rotation was on these. This one was continuous chlorine. And then the other one for eutrophication, people are always worried about phosphorus, how much phosphorus in the water. Well, all of them were very low. We had some that had some spikes to them at different readings. This one had 9 readings out of, I think 100 and some samples. But all of them were below this 0.25. We actually compared this to the phosphorus in the Rush River, the Maple River, the Elk River, and some of the other ones. And it's about 10 to 30% below what's in the rivers. Because most phosphorus moves with surface water. So tile's not good for, you lose nitrogen, but you keep the phosphorus. And phosphorus is one of the big reasons for eutrophication. And remember, I kept talking about sulfate. On those 5 sites, over 60% of the total dissolved minerals in the water were sulfate. The other ones were less. These were the 2 sandy sites. So sulfate comes from those glaciers and all the runoff that came and got deposited over in this area. And just to show you over the period, I got one example here. This is the total dissolved solid, the red bars. And over the 4 years, you can see it dropped. It was going down. So the tile was slowly removing those salts above the tile. But the nitrate nitrogen pumps are during the growing season, usually in the springtime, in June. That's when we had our highest levels. Makes sense, right? When you put nitrogen down. May and June, right? So we get a spike then, but then it drop off, and sometimes in the fall we get a bump too, because you get spring or fall rain. So that kind of concludes my presentation. And if there's any questions, it's been a kind of a general overview or everything, but if anybody got any questions, I'm sure people are going to answer. I'm sorry, I don't have any data for Devil's Lake area. We didn't have any projects for sampling up in here. It would have been really nice because this is a whole different type of you might say, formations and geology up here. And I suspect that you have some of the same water quality problems that's farther east. Any questions?